Hey everybody, Jeremy Waddell, author of Theory of Cardiology. I wanted to talk about this image here that is on page 38 of your book. This image is in the section talking about cardiac output. And so keep in mind that when we talk about um, cardiac output equals stroke volume times heart rate. And so if stroke volume we measure in milliliters, and heart rate we measure in beats per minute, then you can see how cardiac output then becomes mils per minute. Now, if when we talk about cardiac output, we're referring to the amount of blood that the left ventricle is ejecting into the aorta every 1 minute. And so when we take a formula like this, stroke volume times heart rate, there are a few different things that we see on this image here that again is on page 38 of your book. Now notice that heart rate is up here, so that's that dark kind of reddish colored line, and then stroke volume down here is the yellow line, and you can see over here we have the actual scale for each one. So notice that if you put a patient on a treadmill, you get them walking, you start getting their heart rate up. You'll see essentially how this heart rate line is doing here. The heart rate is just going to kind of continue to gradually increase somewhat in a straight line. It won't be perfect, but it'll be close to it. So notice here this patient had a resting heart rate somewhere around 65, 70. And then this patient was put on a treadmill, they start walking for some amount of time, and this is what we're going to see their heart rate do over time. Now, stroke volume, which is also starting kind of the same point down here at, 40, 45 milliliters. And so as the patient is walking and they're exerting themselves, all the skeletal muscles start screaming that they need more oxygen. So we need to basically perfuse these muscles more. We need to get more blood to them in order to get more oxygen to them. And so when this starts happening, you'll see here that stroke volume is going to actually start to climb very, very quickly, because once that heart rate starts going up, the heart detects that quickly and says, hey, we need to really squeeze harder, let's pump more blood. So going back to our formula of cardiac output equals stroke volume and times heart rate. Notice here in this example, in this very first kind of light blue colored zone over here, stroke volume is going up, but so is heart rate. And since both of them are climbing very quickly, and then we're going to actually multiply them together, you can see that cardiac output is going to go way up at this point, because both numbers are getting bigger and we're just multiplying them together. Now at some point you can see right in this area here how stroke volume begins to kind of start to flatten out, and by this middle zone that we have here, this darker blue color, you can see that stroke volume has flattened out. Essentially at this point the heart is squeezing as hard as it can. It has a fixed amount of space, there's a fixed volume, and regardless of how hard the heart wants to squeeze, there is some amount of blood that's just the absolute maximum stroke volume. And so at some point we cross over this line here and we hit this point where stroke volume has maxed out. It's not going to go any higher, but heart rate is continuing to climb. So stroke volume times heart rate again. Notice that your stroke volume is now flat, but your heart rate is climbing still, so your cardiac output is going to go up. Now, it's not climbing at near the rate that it was in that first zone, but cardiac output is still going up. However, this is now much less efficient because it's going to take a greater increase in heart rate to cause cardiac output to go up, the same amount as it would have over in that first zone, because stroke volume isn't going up. Now, right around here, right at the end of this blue zone, the defining feature of where this line falls is that stroke volume is now going to start to go down. And the problem that we're running into here is that heart rate eventually affects diastolic filling time. So remember that systolic time, so how long the left ventricle squeezes for, doesn't change. I don't care if your heart rate is 50 or 150, systolic time doesn't change. And so if you're listening to someone's chest with a stethoscope, when you hear the lub and dub, everything between lub and dub, so let me write this here, everything between lub and dub is ventricular systole, but then everything from dub all the way over to the next lub is going to be ventricular diastole. So here the ventricle is relaxing. And so the way that our heart rate speeds up is we actually have to shorten our diastolic time because systolic time doesn't change. The time from lub to dub does not change. So a very tachycardic patient, someone with a high heart rate, is going to go lub dub, lub dub, lub dub. A slower patient, someone who's bradycardic, is going to go lub dub, lub dub. So it's that diastolic time that changes. And so when we mess with diastolic time, we mess with filling time. And so if the heart rate continues to climb and we're getting up into these extreme numbers up here, you can see where here at some point stroke volume starts to suffer for it. Why? Because if you only give the heart enough time to fill to get in, let's say, 20 milliliters of blood, and then it's time to start squeezing, your maximum stroke volume is now 20. And so there is some point, and it would be, way up here somewhere for this patient, kind of right in there, where the heart rate is going to get so fast that diastolic filling time is essentially gone and stroke volume at some point drops all the way to 0. So if cardiac output is stroke volume times heart rate and stroke volume goes to 0, I don't care what your heart rate is, your cardiac output is now 0. And so this is the actual theory of why patients in VTAC and VFib and these other really fast arrhythmias, this is actually why they go on to not have a pulse and code. It's because they've got so fast on the heart rate that stroke volume has hit 0, therefore cardiac output has hit 0 and they don't have a pulse. So how do we kind of define these zones? The first zone is when stroke volume is increasing. The second zone is when stroke volume is flat. And the third zone is when stroke volume starts to decrease. Now, where do we find these things? Maximum heart rate is roughly 220 minus age. So let's say, you're 35 years old. 220 minus 35 is going to give you not 190, 185. And so at 185, that's when roughly somewhere, give or take 5 or 10 points, is going to be roughly that spot right there for someone who's 35 years old. Now, if we get someone into this third zone out here, what we have to start worrying about is that we're taking away their diastolic filling time. They're just going to get less and less cardiac output at this point. So when we do stress tests on patients, we're typically shooting for somewhere around in that area. And that is roughly 220 minus age times 0.85, or 85% of that maximum heart rate there. So that's the number that we're kind of shooting for. Now, if we look at this image here, I think it's just like a page over in the book. I kind of used an example here, and I think this was a female. She was somewhere around, I think, 70, 75 years old. But notice that if we take her heart rate and we take her stroke volume and multiply them, we'll get cardiac output. And so notice that at a heart rate of 60, this lady had a stroke volume of 40, giving us an output of 2.4. Nice and low, she's at rest, she doesn't need any more than that. Now, if we put her on a treadmill and we get her heart rate up to 100, stroke volume jumps to 90, right? Because now she's doing all this work. we now have a cardiac output of 9. So notice that about a 50% increase in heart rate gave us about a 3 to 4 times increase in cardiac output. So we're in that very first zone. We're very, very efficient. Heart rate goes up, stroke volume goes up, and so cardiac output goes way up very quickly. Now, then here, notice at a heart rate of 140, so we jumped up by about 40% here, but notice that our stroke volume has maxed out at 90. That's all her heart's capable of doing. So that tells you that at this point we're in that middle zone where heart rate is continuing to go up, but stroke volume has flattened. So notice here we had this 40% jump in heart rate, but we only got an extra 30% or so increase in cardiac output. So here the heart rate has to go up drastically to get any more output because stroke volume isn't going to move. Now then this individual here was hitting max heart rate, essentially was around 150, and you can see here stroke volume's nice and flat at 90. Cardiac output was at 13.5. So we went up 10 points, but cardiac output barely moved. Now remember that earlier we said max heart rate was 220 minus age. And so being that her ideal cardiac output where she maxed out was at 150, this patient was about 70 years old. So if we keep going, right, increase the heart rate 10 more points, now we're entering that third zone where now cardiac output is going to actually start to suffer. And now you can see that cardiac output is down to 12.8. So notice here that a heart rate of 140 and a heart rate of 160 both produced roughly the same cardiac output for us. If we increase further, we're starting to get into that third zone, right, where stroke volume just kind of dropped off like that. And so, you know, at the 160 mark, she was probably still somewhere up in here, but by 170, she's getting over here, and you can see that cardiac output is now all the way down at 10.2 at a heart rate of 170. Notice that 10.2 is not that much better than 9. So in this patient, a heart rate of 170 and a heart rate of 100 generates roughly the same cardiac output. And so there is some point where if we took this up to 180, you know, maybe the cardiac output would be like 9, you know, something like that, you know, and so you start to see how as heart rate goes up, it becomes the equivalent perfusion of the heart rate going down. The higher we go on the heart rate, the cardiac output will match something low, and so at some point, you will have a heart rate somewhere way up, you know, 2 to 300s, where the cardiac output will equal whatever you were way down there at 0. And thus why people with really fast rhythms do not perfuse very well. So that's it for this one. There are plenty more coming just like it, so take a look on theoryofcardiology.com for more presentations on topics from the book.